Hello, this is Pre-Calculus. Calculus, AP Calculus, AB, Section B, Unit 2, Lesson 7, the trapezoidal rule. We're going to present one more method for finding area. We've already learned LRAM, the left rectangular approximation method, and RRAM, the right rectangular approximation method. And we've used the MRAM, the midpoint rectangular approximation method. The one we're going to look at today is the trapezoidal rule. There are others. There are quadratic approximation methods and various other ones out there as well. Cubic splines or cubic approximation method. Lots of different things out there here. However, the rectangular approximation method is all that is necessary for defining an integral when you're talking about taking thinner and thinner slices. Where this discussion of Riemann sums and various techniques comes in is in computers and approximations, which methods get to the most precise answer the quickest. These discussions were much more important before the days of computers when much of this was done by hand. And so the idea of doing thousands of rectangular slices by hand was just not practical. All right, that said, let's go ahead and take an example here. I'm going to bring up Desmos. I've set up a problem. I've got the polynomial function y equals negative quantity x minus 2, quantity x minus 16, quantity x plus 1. Between the boundaries of 3 and 15, I'm going to find the area under the curve between those points. I've got a table of values at the points 3, 5, 7, 9, 11, 13, and 15. So that's 7 slices. If we were to use the LRAM method, I would take the first rectangle and use its height and width. So I would do 2 times, and then 52 plus 2 times 198 plus 2 times 360 plus 2 times 490 plus 2 times 540 plus 540 plus 2 times 462. And then I would leave off the last one because we're using the left boundaries for the boundaries. Now, you may notice every one of them has a 2, so we could have simplified things by doing this, doing 2 times, and then just add 52 plus 198 plus 360 plus 490 plus 540 plus 462, okay, and get the same answer. That's LRAM, and RRAM would do the same thing, except it would ignore the first one and start with the second. 198 plus 360 plus 490 plus 540 plus 462 plus 208, and this time we include the last one. So that's RRAM. What I'm going to do here is I'm going to average the two, 4204, and I'm going to do this for interest's sake here, because there's a surprising result after we do the trapezoidal method here. 4204 plus 4516, all divided by 2, and averaging, the average is 4460. You're going to see that number again. Okay, but let me take a screenshot of the graph, and we're going to talk about the trapezoidal rule. Okay, the trapezoidal rule. And it really amounts to this. What we're going to do is we're going to, instead of using a rectangle that's a rectangle, we're going to use a trapezoid. And it's a right rectangular trapezoid, meaning it's built off of verticals. So let me draw the verticals. Okay, so we've got this vertical here. Okay, and let's change the colors to darker green here. There we go. Okay, all right, and here, and here, and here. And here, and I'm going to sketch on this here in just a moment here, talking about the right rectangular method. And I also want to talk about over and under approximations. Okay, If I use the LRAM method, I use these rectangles. And you can see there's all this leftover space, empty space that's not being counted. Empty space. Here we have too much, so we would say this is an over-approximation and too much. Now, as to whether or not the LRAM represents an over-approximation or an under-approximation comes to whether the area under is equal to or more than the area over. I would estimate this is probably going to be an underestimate for LRAM. And then if you do RRAM, the rectangles look like this, right? And all this extra space over the function here, we're overestimating. So LRAM or RRAM overestimates when the slope is positive, underestimates when the slope is negative. Underestimate, underestimate. And again, it's kind of hard to say. Well, I'm going to say this is probably going to be a slight overestimate. Okay, and averaging them is a way to overcome that over-underestimate, but and you would expect the average to be a little bit better. But what we're going to do is we're going to now, instead of rectangles, we're going to do trapezoids. So we're going to connect the dots. We're going to connect the dots with a straight line. Now in this particular trapezoid right here, you can see there's just a little bit of space between the straight line and the curve. So this trapezoid would represent a very slight overestimate. Okay? If I go to the next rectangle here, this one is going to be almost exactly on, right? This one, notice now, is going to be a slight underestimate. And you notice it has to do with the curvature. When we are concave down, the trapezoid method produces an underestimate. When we're concave up, the trapezoid rule produces an overestimate. We actually have more area than we need. Okay, this definitely is an underestimate. We've got some space, some white space between the trapezoid and the curve. Okay, and so this would be an underestimate. And this would be an underestimate, all because it's concave down. But what is the area of one of these trapezoids? Let's take this example here, right here in the middle. Okay, and we'll get some values here. 1, 2, 3, and 4. So the tables, 1, 2, 3, so 7, 360 and 490. So this is 360, and this is 490. Okay. And here's the area of a trapezoid. The area of a trapezoid is 1/2 the height times the bases added. Okay, now in this case, you got to think of the trapezoid being turned on its side, because that's with it like this, right? Base 1, come on. Base 1, base 2, and height, right? Where this is a right trapezoid, one of the sides is vertical. Okay, turn it on its side. And now this is base 1, this is base 2, and this is height. Okay? So in this particular case, the area of this trapezoid is 1/2 of height, that's 2, right? From 7 to 9. 1/2, 2 times the sum of the base is 360 plus 490. Okay? So 1/2, 2 times 360 plus 490. Let's go ahead and do that in Desmos. Okay, so I'm just going to insert here expression, but I want it up near the table here because I want to see the table. Okay, so the first trapezoid is going to be 1/2 of 2 times 52 plus 198 plus 1/2 of 2 times 198 plus 360 plus 1/2 of 2. Now, by now you should be noticing they all have 1/2 of 2, right? So do you think we can factor that out? And the answer is yes. So let's simplify it that way here. We can factor that out. So 1/2 of 2. I'm gonna leave it like this. I know 1/2 of 2 is 1, but I'm going to put it right here because this is kind of the general formula for a trapezoid. So it's 52, and I'm going to put a second pair of parentheses, plus 198, plus 198 plus 360, plus 360 plus 490, plus 490 plus 540. 490, let's try that again. Plus 490 plus 540 plus 540, no, I keep forgetting the parentheses, 540 plus 462 plus 462 plus 208. Okay, now that's all of them. I'm going to expand this and see if we can simplify this again. You may notice something. The 52 appears just once, but the 198 appears twice, the 360 goes twice, the 490 goes twice, the 540 goes twice, the 462 goes twice, and the 208 goes once. So we can even simplify this a little bit further, and I believe the lesson does this here. So here's the shorthand notation. By the way, if you don't remember the shorthand, just remember use the trapezoid formula for each trapezoid separately. But it is nice to have a shortcut here because you are going to be doing a few of these. Okay, so what you do is you list the first, 52, and the last, 208, and then you go 2 times all the others. 198 plus 360 plus 490 plus 540 plus 462. Okay, now the answer is 4360. Now it's kind of interesting here is that 4460, 4360. Ooh, I wonder if I made an arithmetic error here. Let's check. Because my experience has shown me that the trapezoid rule comes out the same as averaging LRAM and RRAM. And I might explore that a little bit more. That really isn't part of the lesson. But 52, 208, 198, 360, 490, 540, 462. Okay, 52, 198, 360, 490, 540, 462. 198, 360, 490, 540, 462, 208. Yeah, it looks like that's the right one. 42. Ah, there it is. There it is. There it is. 4204. There we go. There we go. That was right there. I had a 44/4. 4404. So it's interesting that if I take LRAM and RRAM and average them, I end up with the same as the trapezoid. I'll leave that for you to explore, but there is a mathematical reason. Try setting up the two formulas and figure out the generic form of LRAM and RRAM and compare it to the generic form for the trapezoid rule. All right, so just in review here, the area of each trapezoid is 1/2. The width, that's kind of the delta x, the width of each bin, times the 2 f of a sub I and f of a sub I plus 1. So in other words, it's delta x, it's the width of the bin times the two values from the boundaries, the two function values from the boundaries, 1/2. Okay? And that really is the big idea. Hey, what's the big idea?